Hello everyone. How's everyone today? I hope as good as me. I'm doing fine. And today I'm going to be discussing a little bit of the Peter Bill debate that we had a couple weeks ago. And specifically, I'm going to be analyzing the slit experiment that Peter challenged. Okay. And specifically, I'm going to go over I'm going to review the slit experiment, and then I'm going to go over some of the questions he put up regarding the rope model of light. And we're going to see how it goes. I'm going to look at these two issues. So let's go with a review first of what Peter was trying to do the other day and where we have our differences. Here's the issue. The issue is that, let's see if I can get this up there. Here's the analysis, again, of the debate. And what were the problems? Well, the problem with the slit experiment was that he claimed that he handled one electron at a time. Okay, now he didn't do the experiment. He's just saying, he's just speaking for Tanamura, who was one of the persons who handled one electron at a time when he did the slit experiment. And Tanamura really did it 13 years after Merli, an Italian who headed an Italian group. And they had done it first, but for some reason they always give credit to Tanamura. I have no problem because either way, I think it's nonsense. Anyways, and I'm going to, summarize that. We discussed that last week. I'll just go over it real quickly. Tanamura says he handled one electron at a time. If so, he's got to illustrate his atom. That's what I think he's got to do. If an electron is a wave, that's different than if an electron is a discrete particle. And we need to know what his atom looks like before he goes in there and, claims that he handled one electron at a time. If the electron is an orbiting bead, he's got to determine that unambiguous. He's got to tell us for sure, that it's a little bead, because we need to know, what he emitted and what he received. So if he's going to say that he emitted an electron bead and he detected an electron bead at the screen or at the detector, well, the next step is he's got to identify the medium that keeps the electron bound to the nucleus. In other words, he's got to draw the atom for us. He's got to tell us, in this case, I put a little picture there, he's got to tell us what the green stuff is. In other words, if this is his model of the atom, and it is, because that's what Peter essentially illustrated, then he's got to tell me what that green stuff is. And he went through this rigmarole of saying, that it was a potential. And a potential of what? Well, a potential of a voltage, and that it was and I said, that's not a physical object. And so he went on there saying it was a fabric and fabric of space, and he just kept changing the words. That's all he did. He never identified that green stuff. Specifically, he couldn't tell me whether that green stuff remains globular in that case, or circular if you prefer, when the electron goes away. I mean, what happens to that green stuff? Does it vanish? Is it still there? All these questions need to be answered before anyone can claim they handled one electron at a time for the slit experiment or for whatever, okay? Okay, so that was our starting point. Again, if the electron is an electron bead, and then somehow it morphs into a wave, or vice versa, if it starts being a wave and then somehow morphs into a discrete bead, we need to see, or we need to understand the mechanism by which one converts into the other. How does particle discrete particle morph into an extended wave? How does an extended wave collapse, as they say, to a particle? We need to see this. This has to be part of the theory. Okay, so you can't just wish that away and say, well, I'll just sweep that under the rug and let's continue. No, this has to be clarified. Okay, so that was our starting point. Okay, what was the real problem? The real problem is that we have three versions of what electricity is on the table. The first one is the one that classical mechanics has had for many years. I'd say at least since the 19th century. So we're talking about at least 200 years. Beginning somewhere around the days of Faraday. 20s and 1820s, 1830s, 1840s, thereabouts to today. And the idea there was, that developed in the 19th century as the electron, eventually, was that an electron goes from atom to atom. In fact, we still have that notion today, and many use that and claim that you need a conductor, to have electrons go across. Quantum has invented something in the 1920s called an electron gun, and what they claim now is that an electron does not need a conductor. Or you can put that in different terms. You can say everything is a conductor. It's just a matter of how much voltage you put between that insulation, and everything eventually becomes a conductor. So there are different ways of seeing this. We have a problem with that, very serious problem with that. And so let's go with the first one. Here is the typical, mechanical, what do I want to say? The classical mechanic version. And that's the, here you have a chamber, okay? You have all these atoms, the red ones there. We're going to put them static for now because we're not so much interested in little details. The bottom line is that electricity is the flow of current, which are those little blue balls, those electron balls, which are going from atom to atom, from the cathode to the anode. Okay, very simple. So we assume that we have a bunch of atoms in there. Okay, the electrons simply go from one atom to the other, from one side to the other. That's the classical mechanics or 19th century version of what an electron and what an atom might look like. Really, it was beginning of the 20th century, but timing here is irrelevant. Okay, so what is the problem? The problem is that now the quantum folk came up with something different. They said, look, we've got an electron gun, and we're just going to shoot electrons across the divide, across that chasm. And we don't need a conductor. We can send it through empty space. And that's what they think they're doing. And that's essentially what Tanimura thought he did. And that's what Peter thought that Tanimura did, because that's what Tanimura claimed that he did. Okay, so that's how that goes. And so essentially Peter accepted it at face value, said, how can they be wrong? They detected one electron at a time. Apparently they've been shooting one electron at a time. And here you have the model or the illustration, little GIF there, video showing how the electrons go from the hot cathode. You heat up the tip and you shoot these marbles across empty space. Fine, what's the problem with this? The problem with this is that if we pump the chamber down, remember this is a chamber, we have gas coming in from one end and we have the other end or an outlet connected to a couple of pumps. They could be, a mechanical pump in series with either a cryo or a diffusion pump. So we're going to pump the chamber down, say to -7 range, which is typical range that I worked at least with. I'm familiar with that range. And we're going to pump the chamber down. And what happens? If we pump the chamber down, we have removed all the obstacles that the electron is going to bounce against. And by doing so, we should get a higher current. We should get something that looks like this. Okay? That's what we should get. Why? We removed all the atoms against which many electrons are bouncing. And the mean free path has increased. So now we should get more electrons. In other words, the electricity, the current should go up. This is not the case. Any person who has any knowledge of anything, who's worked with vacuum pumps and with vacuum chambers and with electricity, will tell you that this is not the case. Our experience shows that this is not the case. And if we are to use Mr. Karl Popper, not that you should, but if we are to use him, this falsifies the electron gun notion that quantum mechanics has introduced. Okay, it falsifies it in the sense that we're saying this is not the case. If you remove material from the chamber with the same temperature and with the same voltage, you will get a lower current. In fact, you may not get any current at all. You do need to increase the voltage. And the reason for that is, again, that you need some conductor in there. By removing all conductors, for example, if you could possibly, right, evacuate the chamber completely so that there is no atoms in there whatsoever, you will not get a current, period. Okay? So those people who think that they're shooting electrons across empty space, like the electric universe, these people think that electrons just fly through the plasma, you know, the enormous amount of plasma that fills space between galaxies. You know, they think they're shooting electrons across this enormous chasm, this divide, and that it's these electrons that hold galaxies together because they don't believe in gravity. Okay, so they think it's all done with electricity. And the quantum folk don't propose that for the universe out there, but they do propose it for their chambers. They propose the same mechanism. They're saying if we remove the atoms from the chamber, we should get higher current because, you know, the mean free path has increased. That is for sure not the case. You can take that to the bank. Okay. So that's my criticism of what Peter proposed and what Tanimura, by extension, proposed. So you can get rid of all that nonsense right now. Okay, there is no such thing as an electron gun shooting bullets. And so what do I propose? What's the third option? We have electrons going from atom to atom. We have electrons just flying through empty space. Okay, and then we have Bill's rope version, rope hypothesis version, and that's a series of atoms. Here I just put a single atom just for the sake of showing the mechanism. Okay, obviously this is a little more complicated and we're really talking about molecules, etc., etc. Here I just put a whole bunch of atoms. They're bound to each other, or they're merged. We have merged electron shells because that's what it is. The atom is under the rope model, and these merged electron shells just twirl in place. So what you have is essentially a torsion going from cathode to anode, okay? And all we have is really clockwise and counterclockwise. That's all Mother Nature understands. She doesn't understand negative and positive. She understands counterclockwise and clockwise. That she does understand, and because that's physics. And so here you have the version from the rope model, okay? So you have those three models. One more time, let's go through them real quick. Here's the classical model, okay? Little beads going from atom to atom. You have the quantum mechanics, which is little beads going through empty space, no atoms, no conductor necessary. And you have the rope version, which is, you know, what I say, a serpentine twirling in place. What you have is all these atoms just bound together and twirling in place, actually molecules, okay? Okay, so that's where we stand today. Those are three models. It's up to you to figure out which one you like the best. Okay, that's what we got to do here. Okay, so what's the issue with Tanimura? That was one issue. The other one is that Tanimura does a little sleight of hand, which is very common to do in quantum mechanics, and it goes something like this. You know, what Tanimura did, he says he emitted electron waves. He said coherent electron waves from a sharp field emission tip, that's a gun, okay? They called it an electron gun, field emission, that's what they do, were sent to an electron by prism, okay? So that's what he sent. What did he observe? Well, he observed single electrons. In other words, at the detector, he detected, or there you see the picture. He detected these interference fringes on the wall. He put a detector there, and essentially he said he could collect single electrons one at a time on the screen. And he says, what else could it be? So he says, it had to be one electron at a time because we were able to build the interference pattern one electron at a time. Sounds like an open and shut case, right? Nothing to argue. Well, the first problem is, again, he sent electron waves and he collects single electrons. That's the first problem, okay? Let's go with the second problem here. Here's the setup. Okay, and he says electrons are emitted one by one from the source. This is a lie. This is what he tells the reporters. Okay, this was not in his paper. This is what he tells his reporters. He says he sent them one electron at a time, when in his report he says something totally different. He says, no, what he said is he sent electron waves to an electron by prism. He sent waves, and now he's talking about what? Particles, one at a time, and he's detected one by one as particles at the detector. That's how he says he detected them. Okay, so again, anyone who makes these claims has to do a single thing, and that's draw the atom. Just illustrate your atom. If it's a little bead going around, because you're going to be handling one electron at a time, right? So you can't start with a wave. If you say, you got to choose. Did you pull a wave out of your gun, or did you pull an electron bead? Which of the two did you pull out of your gun? Well, he's to the public. He says he pulled a bead, and in his paper he wrote that he pulled a wave. So we got a problem there. Okay, so please draw your atom. What does your atom look? Does it look like? Does the electron look like a wave that surrounds the atom? Is it a cloud that surrounds? The wave you would think is like de Broglie's wave. It's just a hula hoop, a little undulated hula hoop, right? That's what you think of when he talks about a wave. If the electron is around, the nucleus, it's a hula hoop, and if it's spherical, well, which is the cloud model, Born's cloud model, okay, so now we have two different kinds of electrons. And if the electron is really a bead and the cloud is really the orbital, the region where you can find the bead, now we have a third version of the atom. We have three versions of the quantum atom. It's a little bead that goes around, that's the electron. The other one is the orbital, which is like a shell, which is like a cloud that envelopes the nucleus, and with which they do, covalent bonding and other stuff. So, they're using the orbital as a physical entity. And then there's de Broglie's hula hoop, which is just, integral waves around, the nucleus. We have three versions. Tanimura's got to tell us which one he's going to use. And he can't tell the public, oh, we used the bead, and then he tells the people in the industry, the specialized journals. He tells those folks. He said, well, we really emitted waves. Okay, so keep that in mind. That's important. Okay, so what is the issue? The issue is that Tanimura believes he's dealing with cannonballs. That's how quantum does its stuff. It shoots cannonballs, makes holes with cannonballs, right? That's how Tanimura says that he made the holes on the wall, or how he detected one ball at a time at the detector or at the screen. He built his interference fringes one ball at a time, one shot at a time. And then we have, Bill Gates' different version, which is the drill bit twirling in place. This is another way to make holes, a little more modern way, by the way, than, you know, shooting cannonballs. I guess Tanamura is still, you know, in the what is it? He's still in the old age and you know, fighting with cannons and whatever. So he's got that maybe in his mind. I don't know. All of quantum is still in the 19th century in that sense. Okay, so we have drill with twirling in place. One more time, here it goes. That's the model that I propose, and you say, well, how do you relate that to the rope model? Okay, so here it is. Here is electricity and magnetism in both of them in one single image. Okay, we're saying that electricity consists of a row of atoms, really molecules. We're just going to deal with atoms for now, and they're twirling in place. They form a serpentine. They're all blended with each other, so they form this row, and they're twirling in place. Okay, and because they're twirling in place, they swing threads around it. The rope that unites all these atoms, the two threads are released, and they swing around the twirling atoms. And those gazillions of threads that are twirling around, that's going to be the magnetic field. And as you can see, the threads are spinning or swinging at 90 degrees to the flow of electric current. So we're consistent with experience and with observation. And the orthodox version is the one below, and that's you know, the flow of beads. So we have two different mechanisms. According to Tanamura in quantum mechanics, current consists of a flow of beads, okay, and along a wire. And in the case of the rope model, we have a twirling serpentine. That's what I call those merged electron shells, and that swing threads around themselves, and those threads will form the magnetic field. Okay, so that's the model that I'm proposing. And we can see with that why we have voltage. We know that current, again from experience, current flows spirally around a wire. And what quantum does is say, well, we have positive at one end, negative at the other end. We call it voltage. We don't know what voltage is. It's a potential, whatever potential is. It's a difference in potential, whatever that means. And here we say, look, you know what it is you have the entire serpentines. They're either clockwise at one end, and they had better be counterclockwise at the other end. No matter what wire you use in the universe, if you twirl a wire at one end clockwise from the other end, you will see it counterclockwise. And that's the issue. That's what voltage is. Voltage is not a potential where you have more water here and less water there in an inclined plane where water runs down the hill. That's not voltage. Voltage is clockwise and counterclockwise of two ends of a wire. That's what it is. That's what Mother Nature understands. And again, until they define what voltage is, we don't have that, you know, and not define it, I mean illustrate it. We don't have a notion of what these people are talking about in terms of electricity. What do you mean voltage? What is voltage? You say, well, it's a difference in potential. Yeah, what does that mean? Just mathematics? Same 5 volts here, negative volts, 5 volts over there. What does that mean? In physical terms. Again, they have to illustrate it. We don't want any math. We don't want any numbers. What we want is a picture, a photograph, a movie. Okay, that's what we want. We want to see something with our eyes that's not an equation or a number. Okay, so what does that take us to? It takes us to the Slit Experiment. Here's my version of the Slit Experiment. Based on that, and I'm using Tanamura's picture there. What it is essentially is that the serpentines are twirling in place, and the plates there. See the slit here is formed between one plate and the other plate with the filament in between. Okay, so the slits are, in this sense, right, is where the green serpentines are moving around. Okay, that's going to be the slits in terms of electrons. Okay, in terms of electricity. And what we're saying is all we're doing there is just spinning electrons or spinning electron shells, right, that are merged, and we focus them on a screen or on a detector, and that's where we get the interference, because they either are in sync or they're out of sync. They're in phase or they're out of phase. That's all it is. Okay, so the model is very simple to understand once you have a picture of it. Okay. Okay, so what are our conclusions? Well, here are the conclusions. I'm saying the electron gun misleads mathematicians to believe that electron beads fly through the vacuum. That is not at all the case. As an ideal vacuum is a perfect insulator. Electricity requires a conductor. If electricity consists of a flow of electron beads, the proponent must illustrate the atom. If the theorist illustrates the electron as an orbiting bead, he needs to illustrate the medium that prevents the bead from flying spontaneously out of the atom. Neither potential nor voltage, as Peter suggested, qualifies as a fabric or as a physical medium. The word fabric is really very misleading, and neither voltage nor potential are fabrics. And fabric is not a physical object either, by the way. You can say, what is it, a fabric of cloth? Cloth, you can say that fabric is what a cloth is made out of. It's all these, threads or strings or whatever that you sew together. That's a fabric. So to say that, a voltage is a fabric or a potential is a fabric is meaningless, totally meaningless. Or space-time is a fabric, same thing. Voltage is defined as a difference in potential, and mathematical physics has no physical interpretation for voltage. Therefore, it is irrational to state that a concept such as voltage binds the electron bead to the nucleus of the atom and physically prevents its departure. Period. Claims that lab technicians have handled one electron are assumptions, which they've turned into proofs. Claims that the Slit experiment was performed by sending one electron at a time cannot be regarded as scientific until the theorists illustrate their version of the atom. And the quantum physical interpretation of the Slit experiment is unscientific, because the electron is regarded to be a wave at emission and a particle at impact. Quantum does not explain the mechanism of this magical conversion. And that's what they have to do. If they're going to say that they handle one electron at a time, well, draw your atom and show us what keeps it bound to the nucleus to begin with. The electron keeps the electron bound to the nucleus to begin with. We need to see that, okay? Then they can move on from there. Otherwise, they don't even have a theory. They don't have a case. Okay, but we didn't stop our discussion there. We had a discussion about the rope model. And the problem there was that, unfortunately, Peter did not do much of a research on the rope model, and that took away from the discussion because, there was not much to discuss when he didn't understand some of the basics, some of the fundamentals of the rope model. More fundamental yet, I wanted to get into, the foundations of physics. What is physics about? Do we need an object? And he kind of brushed that aside. Well, he did address that, but he didn't do a good job of that. On the one hand, he said you need an object. Then he starts talking about, a fabric of potentials or a fabric of space-time or a fabric of, voltage. And again, that means he didn't understand what we mean when we say that you need an object in physics. That's none of those qualifies as an object for the purposes of physics. And the dialogue went something like this. Okay, here it is, so that we're all on the same page. That's a little too big. Let's see if we can shorten that a little bit. Okay, so it goes something like this. So Peter, you have your magnetic rope and you have your electric rope. I have no idea where he got that or what he's talking about. Is this accurate? No, it's not. That you have two ropes and that's when they unwind and they come back together. Again, I don't know where he got this. He obviously did not do a minimum of research on the rope. You would think that, all he did was send me 4 papers and said those 4 papers challenged the rope model because I cannot explain those experiments with a rope, but he never figured out what the rope model was about. Or are they 2 separate ropes? Does rope conform with known physics? And I like that question because, and that's the one I want to address specifically. Does the rope conform with known physics? So let's look at that. Does the rope conform with known physics? And I'm saying, yeah, the rope model can explain many features, especially of light. And it can explain straightness, why light travels straight or rectilinearly, right? It can explain undulation, why light is undulatory, why it's wavy. It can explain why light is so fast. And it can explain also why light always meets its target. It always finds its target no matter where. I mean, you can move the moon anywhere you want and it'll stay within vision of your eye. And you say, how can that be if the moon is moving, you know? And maybe the moon doesn't move very fast, just 1 kilometer per second around the Earth. But you can take some you know, like Halley's Comet probably moves faster. I have no idea how fast Halley's Comet moves, but I think it moves faster. And you can see it. And it's not always at the same place. You see it instantaneously, like when you're flying a kite. You know, you scan the kite around the sky, and you always see it. Miracle. Well, yeah, because you have the string tied to the kite. Wherever the kite goes, that's your line of sight. And that's what we're saying happens with the rope model. You're essentially flying a kite. Okay, you get a direct connection at all times with whatever moves out there. And so let's go step by step. Here's the issue of speed. Okay, here's why the rope explains, you know, the speed of light, why it's so fast. Okay, and here we have, at least as compared to the transverse wave. Transverse wave and longitudinal waves, you know, they're very slow compared to a torsion wave. And you can show this to yourself, you know, just take any rope, your grandmother's rope, tied tightly between two walls, and just put two clothespins at the far ends, and just push one clothespin, the other one will move instantaneously. That's how fast a torsion wave is. The tighter you have that rope, the faster that torsion wave, we can call it that, you know, moves from one end to the other of that rope. In comparison, you know, one-way waves, such as longitudinal waves and transverse waves, they're very slow. And it turns out that a longitudinal wave is even faster than a transverse wave. As you can see there, the turtle beats the poor little snail. And you say, well, is that really true? I mean, is a longitudinal wave faster than a transverse wave? Yeah. And here it is. Here we have a case that you can also take to the bank. Okay, cash it in. During earthquakes, they've measured longitudinal P seismic waves. They're known as primary seismic waves. They call them P waves. And they reach you 1.7 times faster than transverse S waves, shear waves. Okay, the shear wave takes longer to get to your house than the longitudinal seismic wave. Okay, and so, you know, just as a comparison, sound is a longitudinal wave. So if this is the case, if light consists of transverse waves, then when there's a thunder, lightning, you should hear the thunder faster than you could see the light. And that is obviously not the case, because, you know, thunder would be the sound, right? The boom that you hear, that's a longitudinal wave. And the light, the flash that you see, that's supposedly a transverse wave. Well, you know, if we were to follow the analogy of the earthquake, you should see the thunder before you should hear the thunder before you see the flash. And obviously that's not the case. So it's questionable, very questionable, if, you know, light is a transverse wave, because a transverse wave is about the slowest thing we've got out there as far as waves are concerned. Okay, and again, here if you go with the torsion wave, see if I can find it here again. You go with a torsion wave. There it is. Give me a second here. The torsion wave is much faster than either a longitudinal wave or a transverse wave, but it also has another feature, and that it goes both ways. Transverse waves and longitudinal waves are one-way waves. They only go in one direction, outwards. Whereas the torsion, or if it's along an existing elongated agent, such as a rope or a chain or cable, it goes in both directions. And the good thing about it, you can explain entanglement with that, because at one end you're going to have clockwise, and at the other hand you had better have counterclockwise. So entanglement, which is a big monster for the people in quantum mechanics, is a no-brainer in under the rope model. Whatever's clockwise at one end had better be counterclockwise at the other end. Okay. So that tells you a little bit about speed. Now let's see if we can look at straightness. Here's the other feature that the rope model can answer. Here you have a transverse wave, which is what quantum says, or mathematical physics in general says, light consists of. And you can see the torsion there, the torsion wave, not only is it very straight, right? The rope is at least straight, and that means that torsion can only travel undulating, but along a straight line. And the transverse wave, you can't do that. No matter how you do it, the transverse wave is not going to be very straight, and not very fast either. You can see the torsion wave is much faster conceptually. And the other good thing about it is that, the torsion wave is always stuck to a target. The target can go anywhere it wants. And you can't do that with the transverse wave if it's a one-way mechanism, a one-way agent. By the time you send the next wave, the target's no longer there. So the torsion also has that advantage where, it's already connected at the other end, the rope is, and you're just sending torsions along that rope. So it's a much more efficient, much more rational system than the standing wave of quantum mechanics. And here's another version of that, another vision. Let's see, I think it's this one. These two guys are doing a transverse wave, okay? They're using what is known as a standing wave. Note that first, the guy has to hold on, the guy on the right over there, the young guy, he's got to hold on to the rope. If he lets go of that rope, that's going to sag all the way to the floor. You won't get a transverse wave. That's the first problem. Okay, but let's keep it there. What happens? You can see that the rope is not very straight. It's sagging. It's going all over the place. Absolutely not very straight at all. I'm wondering if light behaves like that when it goes to the mirror, from your face to the mirror. Does light really wobble that much? Well, maybe if you had too many beers it would, but certainly not, by its very nature. Light goes straight, period. And we have to explain that straightness. And you can either talk about rectilinear travel or straightness, either one. I mean, if you're going to talk about particles going from one end to the other, you're going to say, well, they travel rectilinearly. Why would a series of particles do so? And in the transverse wave has the same problem. If it's a one-way mechanism, holding it at one end is already cheating. But even if we grant that, you can see that the rope or that wave is not very straight at all. Is it fast? Well, we already discussed fast. Not fast at all. And then on top of that, they say, well, a transverse wave, light, right, needs no medium. It's the waving of nothing. They say it in two ways. On the one hand, they say it's the waving of nothing. And on the other, they say light does not need a medium through which to travel. So it's a different way of saying something similar, but it's not exactly the same, okay? But essentially is they're trying to avoid a medium because they don't know what a wave is. And a wave is not a noun, it's a verb. Wave is what something does, and that something has to be identified. And what they've done is say, well, we can't identify it, and since it can travel through space, which supposedly is nothing, they say, well, then it's the vibration of nothing. They got rid of the ether. And then on the other hand, they'll say that space is made of particles, positive particles and negative particles. When these particles come together, they become no particles. And then space can also break up into these particles. So you figure it out, what these people are talking about. Okay, and we also have the issue of a wave extending versus, whether the wave travels. Because, see, one of the issues that I have is that these people sometimes criticize the rope model on that basis. They say, are you telling me that the rope, the electromagnetic rope, extends from an atom in the Andromeda galaxy all the way to us? 2+ million light years away, it's extending all that distance? And then the question, the answer to that question is another question. Well, what are you telling me as far as your wave is concerned? Is your wave extending all the way from Andromeda to us also? And if not, does it travel like a little sailboat? Where does the wave begin? Where does the wave end? I mean, they talk about wave packets. What does that mean? That means it shoots one wave, the atom does, shoots one wave, then it waits, then it shoots another wave, then it waits, then it shoots another wave. Is that how it is? And all these little waves travel like sailboats in a straight line to your eye from Andromeda. So we got the same problem no matter whether you use particles. Why did the particle travel all that length of that distance? Think about that. And here's the comparison illustrated. Here's the electromagnetic wave. It's produced by the atom, and so here's the little wave being sent out. And the question: does it extend from Andromeda to us, or does it travel like a little sailboat, a discrete little wave packet? There's your wave packet just being sent. Okay. So which of the two is correct? Does it extend or does it travel? And they have to address that question before they can attack the rope model. And again, if the atom produces a wave, the question is, does it produce a little discrete wave that travels, or are all these waves connected? I mean, whenever you see the wave model, they show many links together. Why? Why don't they show one link at a time? Why do they show a bunch of links connected, like the case up there on the upper left? That's what they show. They show a bunch of links that are connected, a bunch of waves that are continuously connected. And here you can see something different. They in the next one here they show you that the little thing travels as a discrete little bug, a little corkscrew there. And so the question is, which of these two is correct? And they have the same question as the rope model. They can't avoid that question either. And of course, they've never questioned that. They never asked the question to begin with. Okay? Aside from that, we have another problem as a addendum, another aggregate there, and that's that they cannot explain pull with their particles or waves. I mean, if here we have Casimir, my little friend there, and he's throwing rocks at the donkey and pulling it that way. Is that rational? Is that how quantum does it, by throwing stones? Is that how quark pulls on another quark, by throwing gluons at it? And it's more rational to think that you pull on a donkey by pulling on a rope or some kind of extended object that goes from here to there. But to say that you're going to use discrete stones, like in the case of electrons that are being pulled out of an electron gun and shot against the screen or against a detector, Well, then you have that situation there. The question is, can you pull with that same mechanism? See, we can do it. We can do both. We can not only torque the rope and send you light, we can also pull on the rope and give you gravity. These people cannot they cannot justify the particle being, the electron being a particle, first of all, or light being a particle, and then they cannot, with that same ball, produce attraction. So they can't do either. Where with the rope you can do both. Okay, so that's in general my criticism of what we discussed the other day. And all I can say is that, you've got the presentation. It's up to you to figure out which way you're going to go. If you think quantum is rational and you can do it with particles or with waves. I mean, I don't care. You can choose the wave. But you can't, in the middle of the race, change horses and say, oh, I've converted the wave into a particle, because I cannot explain with a wave the impact, the single impact. And then you say, well, how do you explain the fringes? Oh, for that we bring the wave back again. And we have two waves just meeting out of phase on the screen. Well, hold it. Did you have two waves meeting, one perpendicular to the other? Well, yeah, but when they hit the screen, they turn into a particle. And again, that conversion is what's fishy, and again, you should use Karl Popper at that point and say, well, Karl Popper falsifies both of them until you can figure out how to explain that. You can't use the particle when it's convenient for your theory and then convert it into a wave at your convenience also, when it's, when it's handy. And so this is the problem with quantum mechanics. They don't have a rational explanation. They don't have a physical interpretation for the Slit experiment, and they cheat and they say, oh, we do. We do because we just convert the particle into a wave whenever it's convenient for us. We shoot particles or waves. We don't care. It doesn't matter to us. We shoot a wave and then collect a particle, or shoot a particle and then have waves interfere. They can do it either way because they're going back and forth and cheating. With a rope model, it's straightforward. You have, in the case of light, you just have two ropes, and in the case of electricity, if you're going to do it with electrons, well, you have merged shells, and they're spinning in place. And so either way, you can explain it rationally and, with physically. I can make a movie of this. In fact, I have. And so that's where we stand. And so that's my criticism of Peter's version. And again, it would have helped a lot if you would have learned a little bit about the rope model. Okay, so we'll see you on Wednesday, and probably just finishing off on that discussion and get into some other subject by then. We'll see you on Wednesday. We'll see you then. Bye-bye.